complex waves. All right, so complex wave. Excuse me. Where am I? All right, so we know what a complex wave is. We have spoken about frequency synthesis. We have spoken about harmonic analysis. We understand the use of Fourier series. We understand the various components within the Fourier series. And so we're going to pick up on that this evening by looking at power associated with complex waves. All right, so we're looking at power associated with complex waves. So if we have a supply voltage V, and as we would have indicated in the last lecture, the lowercase v indicating that we're dealing with a voltage at a point in time, instantaneous voltage, and the lowercase I, instantaneous current. All right, so we have a voltage V given by V1m sine omega t through to V3m sine 3 omega t, and so on. And it is connected across an impedance. So we have an impedance Z. We have our source. So we have Z. And we have V, and it produces I. All right. Now we do not know what Z comprises of. So it means, therefore, that the phase angle, yes, that's phi, can either be positive or negative. If it's more capacitive, then we know that it will be plus. If it's more inductive, then we know it will be minus. All right. So for our fundamental, we have that as the current component. For our second harmonic, we have that as the component. And for our third harmonic, we have I3m sine 3 omega t plus or minus phi 3 as our component. And bearing in mind, as we said in the last lecture, these phase angles are always denoted in radians. All right. All right. So we have a circuit. We connect our V. We get a corresponding current. What I'm going to tell you is something that you're just going to accept. All right. So the power, the instantaneous power, is going to be equal to the product of the voltage and the current. And we already know that. All right. We know that P is equal to V times I. Of course, we know it's VI conjugate, but for our purposes, it's V times I. Now, when we do that, we are multiplying here the voltage expression times the current expression. And of course, if we're going to expand the bracket, then we would multiply the V1m by all of the I components, and then we multiply V2m, yes, by all the I components. That's how we expand the brackets. So, you know, so we'll have V1m times I1m, V1m times I2m, etc., etc. All right. Now, in doing that, what I said just now, which you will have to accept, is that we will find that P, which is equal to P1 plus P2 plus P3, yes, would be equal to or given by, yes, like harmonics, the product of like harmonics. In other words, when I multiply V1m by I2m, yes, that product is going to be 0. When I multiply V2m by I1, this product is going to be 0. So only where they are like harmonics will I get an output or get a value. So I'll get a value when I multiply those two. I'll get a value when I multiply those two. The third harmonic times the third harmonic for the voltage and the current respectively would also give me an output, so forth and so on. So the point here is that the product of different harmonics will be 0. And so I end up with P1 being equal to P rather being equal to P1 plus P2 plus P3. All right. And P1, 2, 3 represent the power for each harmonic. And the power for each harmonic, we need to be very clear on this one. The power for each harmonic is given by the integral from 0 to 2 pi, because we are doing it for a full cycle. Yes. So 1 over a half times the integral from 0 to 2 pi of V1m I1m. And of course, we have the sine omega t, which will be from the voltage, and the sine omega t plus or minus phi 1 from the current. All right. When we solve this over the range 0 to 2 pi, we get P1 to be equal to V1 I1 cos phi 1, where V1 and I1 are the RMS voltage and current of the harmonic. So in other words, V1 would be equal to V1M over root 2, and I1 would be equal to I1M over root 2. All right, so it's the RMS values. That's important. Any question?
Sir, you can go over the RMS value part again.
All right, so we are saying here that P1, all right, remember we said that the instantaneous power is going to be equal to the sum of the powers for each of the harmonics. Okay, so P1, when we solve this integral, and if you have time, go ahead, be my guest, solve it. All right, when you do that, we're saying that P1 is going to be given by this. All right, that expression. However, V1 and I1 in this expression, yes, are the RMS values of the current and the voltage. In other words, remember V, oops, sorry. Remember V was given by this expression, and I was given by this expression. Yeah. So for the fundamental, V1 would be equal to V1M over root 2. And here, I1 would be equal to I1M over root 2. Amplitude over the over root 2. We're going to do that?
Yes, sir.
All right. All right. And if we look at the second harmonic, we'll get a similar expression. So note the phi 2 and the phi 3 would be coming from the current expression. All right. So it is V2 I2 cos phi 2, V3 I3 cos phi 3. And so when we add the 3, then we get this expression. So for P1, or in other words, for the fundamental, that's the power. For the second harmonic, for the third harmonic. Any questions? All right.
So are you there?
Hello?
Oh yeah, you're hearing you now. You went silent all of a sudden.
Yeah, man, I'm muted. All right. So we have the expression for instantaneous power P. Yep. And we can now look back at something we did in AC circuits.
Quick question, sir. Um, for the power, we look for the on the previous slide. We look for each individual P cos phi, each individual P first, and then put it in the complex waveform.
Not sure I understand the question.
As in, like you have
Your
V1.
background is very noisy. I can hardly hear
I
you.
can't control that, sir. Outer road noises, sir. As I was saying, for the V1 I1 cos phi, cos phi 1, we look for P1 in that terms first.
Oh, but this is P1.
Yeah, and what I'm saying now is we look for P1, P2, P2, and then put it in the complex waveform. As you have it right there. You understand what
When
I'm
you say
saying,
put
sir?
it in the complex form, I'm not sure I understand because
All
we
right,
have
the
already.
final formula right here, so we have P equal V1 cos phi 1 plus V2 and so on, power 1, power 2. Would that be a complex waveform for the power? For the power output, sir?
All right, hold on. Pause. Would you have known the value of phi 1?
Yes, sir.
Would you have known the value of phi 2?
Yes, sir.
Would you have known the value of phi 3?
Yes, sir.
Okay. Would you have known these values? V1, I1.
Yes, sir.
Okay. So if I know these values, what would this give me?
P1.
No. Would it give me an oscillating signal? Or would it give me a numerical value?
Numerical.
So this is no wave expression. These are just adding some numbers.
All right, that's what I wanted to clarify, sir.
Okay. Now let's go back to the power triangle. Remember that impedance triangle that we looked at when we considered R, X, and Z? This is what our triangle looked like. So on the y-axis we had X, here we have R, and here we have Z. And then the phase angle would have been there. That's our phi. And of course, this was 90 degrees, okay? That's our impedance triangle. Based on this impedance triangle, R, which is the adjacent, R would be equal to Z cos phi. But you agree with that? Now,
Yes, sir.
if we look back at this expression, I am multiplying V by I by cos phi. Yeah. Now all I'm taking off here is the V cos phi, and V we know is equal to I times Z. So V cos phi, as we are showing here, V cos phi, the IZ would be V. Yes, we have IZ cos phi. And from our power triangle, Z cos phi is equal to R. So if Z cos phi is equal to R, then it means that V cos phi 1, yes, would be equal to I times R. Because Z cos phi 1 is R. So we have IR. So if I substitute IR into this expression for V cos phi, then I'm going to get I1 times I1R. For this one, I'm going to get I2 times I2R. Yep. And of course, for V3, I'm going to get I3, I3R, which is how we end up with this expression. So I'm just substituting for V cos phi. And in doing that, I get that P is equal to I1R squared, I2 squared R, I3 squared R. We can factorize this. And if we factorize, I don't want to go there yet. If we factorize, we'll get R into I1 squared plus I2 squared plus I3 squared. All right. And by definition, this is equal to IRMS squared. So in other words, the power produced by the complex wave when connected to that circuit of impedance Z, the power is equal to the square of the RMS current times the resistance. So just as we had established when we were looking at AC circuits, that the active power is dissipated in the resistive part of the circuit, it is shown to be true also for a complex waveform. Any questions?
You can go over that again, sir.
I said a lot of things. Be more specific. What is it that you don't understand?
The part where the P is equal to the I square IMS, where it says equal to the.
Okay. Do you agree? All right. You understand the factorization here, right?
Yes, sir.
All right.
Yeah, we know that get the complex rate for the IRMS. The power for the complex rate and the IRMS.
Yeah. P is equal to this. And I'm saying that this expression here, when I factorize, that expression is equal to the RMS, the square of the RMS. From lesson 1, which I had asked you to review, IRMS is equal to the square root of the sum of the squares. By definition, that is the RMS. So if I have I1 squared plus I2 squared plus I3 squared, then it's equal to IRMS squared. So I'm just putting the square root sign on the other side or moving it to the other side. So by definition, what we have here is IRMS all squared. So I can remove all of that and just replace it with the IRMS, which is what we have here. All right, but again, it is tied to what we did in lesson 1. All right. Now, here we are introducing a direct current component, all right, or a DC component. Now, the DC component, as was established in lesson 1, would be the A0. Of course, you know the coefficients from your Fourier series. You have A0, you have AN, and you have BN. So the A0 would not have a sign component. So that A0 would represent the DC component, because the DC, is not fluctuating, it's steady. So that would be the constant in the Fourier series. Again, we know that from definition, yes, from definition, we know that when we speak of RMS, the more classical definition would be the effective value. As if you go back to how we define RMS, not necessarily in this course, but from your physics, we define the effective value as the value of the AC, yes, which is equivalent or would produce the same heating effect as its equivalent DC. So in other words, when we come to the DC and speak of RMS, it would be the same value. So it wouldn't be changing anything. So in this case, it would just be IDC squared plus I1 squared, I2 squared, etc. So the formula, gentlemen, would remain the same. The difference, however, is that if I have a DC component, I would not be finding the RMS value of that DC component. All right, that's the key. Now, the active power that is supplied to the circuit, we know that the active power P is also equal to the apparent power S times cos phi. In this case, however, this phi that we are referring to, note all the other phi's that we have spoken about, I have denoted them as phi 1, phi 2, and phi 3. But this particular phi that I'm looking at would be the overall phase angle for the circuit. So cos phi of that angle would be the power factor of the circuit. So S here would be VI, yes, and of course the power factor cos phi. So we're going back to what we would have done in AC circuits. Okay? Yes, Mr. Thompson.
Sir, so when finding the power, you would have IDC squared plus, or how would you factor in the DC component into it, sir? Because would it just be that value plus the other current square, the RMS value?
Because the DC value, for use of a better word, I mean, it sounds cyclical, well, counterintuitive, but anyway, the DC value is really the RMS value. So there's no, you're not dividing that value by root 2. Again, if you go back to lesson number 1, if you have the DC, that would have been the RMS value. And this is where a lot of persons make the error. So when you put everything under the square root sign, that DC component must not be divided by 2, because it is already the RMS value. So as we were saying,
oh, sorry not to cut it, sir. So if you were to write it in a simpler way, you'd write P equal R times the open bracket IDC squared plus I RMS squared.
No. All of this represents the RMS of the current waveform. But what I'm saying is that prior to this, when we started, we were not contemplating the current having a DC component.
Yes, sir.
You with me?
Yes,
But
sir.
if it had a DC component, we are now saying that the RMS current in finding the RMS current, it will be modified as shown. This represents RMS. You know. This is no RMS. This is RMS. And combined, it gives you the RMS of the entire waveform.
Okay. Okay, sir. Thank you.
All right. So going back to the power factor. So we have this expression for the active power, VI cos phi, and we have I squared R. Yeah? So it means I can therefore find the power factor of my circuit. So the power factor would be the total power supplied divided by the RMS current times the RMS voltage. All right, so this section at the top, the numerator, this would be equal to I RMS squared times R. So you can either do it this way or you can do it this way. Both will give you the same answer. And then the power factor, because when you do that, you'd have gotten P. When you multiply I times V, we get S. And we know that power factor is equal to P over S. All right, active power over apparent power. Any other questions with what we just did? All right, clear as mud. All right, so we move right along. So I don't know if this question is in your lecture notes. If it is, well, not whether or not, I'll give you a couple of minutes to take the question. All right, so let's try and go through this in a timely manner. So what I wanted to hold on. I'm gonna stop sharing for a while. I want to just confirm for me, gentlemen. Do you have this in the lecture notes?
I don't see it, sir.
You don't see it. All right, cool.
I see something like it, but look like some part missing.
All right, no problem, no problem. I'm gonna stop sharing just for a moment. Okay. All right, here we are again. I just wanted to include some slides so we can go through the solution together. All right, so the first thing we want to determine is the Fourier expression for the circuit current. Yes? So in doing that, what we're going to do, and this is supposed to be plus. So this is supposed to be plus, right? So we want to start with just looking at the voltage expression and determine which harmonics we have. I mean, it's not an absolute necessity, but it's good practice. It's good practice. So if you note, we have here 377. And of course, you multiply 377 by 2, you'll get 754. Yes. If you multiply 377 by 3, you will get 1131 and so forth. Multiply it by 4, you'll get 1508, and by 5, you'll get this one. So it's saying to us that this would be your fundamental. So that's your fundamental. This would be a second harmonic. This would be your third harmonic, your fourth, and your fifth. Right? And that's a, I mean, you know, it doesn't take a lot of time, but it's a good check. It's a good quick check that you would want to do. You know, when you're about to take on a question like this. So we have checked, we know what harmonics are there, we know we see the fundamental. So we can now start and make our statements. So the first thing we're going to do is to carry out our calculations at the fundamental. Remember, the objective is to find the current expression. So we want to say that at the fundamental.
Sir?
Yes.
So that would make what we're working with, just a quick check, that would make what we're working with a sawtooth.
I don't know.
Sawtooth wave, since we have all the, okay.
It's, why I say it's possible is that you will not only look at the harmonics that are present, but you'll also have to take note of the coefficients.
Oh, okay. I see.
To be absolutely sure that that is a sawtooth. But then again, you know, I kind of get it because I have the
symbol
sawtooth up in there. Yeah, I kind of get it. But anyway, but that's a good observation. Good observation.
Yes,
all right, so at the fundamental, we have here a capacitor and a resistor. So at the fundamental, omega is 377. So it means that XC is equal to 377. 377. Oh, come on, don't bother with this now. That's 377 times 147.362 times 10 to the minus 6. All right, what does that give us? Of course, all of this to the minus 1. Eh? What does that give us?
Wait, what's that?
Right, I'll work it. That's 377.
Sir, I get
147.362 minus 6.
555.
It's to the minus 1. So that gives us 18.
Oh, you wanted the reactance? Okay.
Yeah, man, the reactance. XC we're working on.
Okay, so yes, sir, 18.
So we get 18 ohms. Now, the beautiful thing about it, because I know what harmonics are there, you know, the others will be quite easy to calculate. All right. So Z is therefore equal to 6 minus J18. So that's Z1, because we're dealing with the fundamental. Yes. So we want to then convert, and as we would have said in lesson 1, we must always be working in radians. So we want to convert 6 minus J18. Yes. We want to convert that to polar. So we get 18.974 at an angle of minus 1.25. Okay, so it means that I1 yeah, the voltage was 60, so we'd have 60 divided by that. So that will give us 3.1623. So the 3.1623 at an angle. Remember, it's now I, and we're dividing, so it would now be 1.25 radians. All right, so that's the first component. So I1 would therefore be equal to 3.1623 sine 377t plus 1.25 radians. Any questions?
Sir, what is that symbol there?
So C, it's for radians. All right, everybody else comfortable?
Yes, sir.
All right. So when I go to the second harmonic.
One more thing, sir. Can I go back? Apostle. All right. Is that a S at front or C1?
Sine
Sine
3.1623 sine 377t plus 1.25. That's just for the fundamental. All right. So
Yes,
we go to the second harmonic. So for the second harmonic, Z, now because it's a capacitor, when I increase the frequency, we expect Xc to be reduced, eh?
Yes, sir.
So because I did this calculation already, I know that it is 18, so at the second harmonic would be half of that. So we know it is 6 minus J9. So I don't have to do the calculations again. I convert this to polar. Yes, I convert that to polar. So we have 6. That gives us 10.8167. Oops. 10.8167 at an angle of minus 0.982. So the corresponding current, so the I2 would be equal to V2 over Z2. Yes. V2 was 30. Yes, so we have 30 divided by 10. Right, so we get 2.77. Let me just use 4 dPs. 35. Yes. Sine 754t plus 0.982.
Sir, I noticed something and I wanted clarification. So the angle that we got, if it was positive, when we would it be the current at the second harmonic then be like in the brackets, would it be 754t minus
No.
the angle?
Remember, V, look at V. What's the phase angle here?
754.
No, the phase angle.
Oh, the omega t, is it that?
No, man.
Sine omega t.
Omega, this is 2 omega t. But I'm saying what's the phase angle for this second, for this? All right. It's not a trick question, but it's 0. So it's
Okay.
754t plus or minus 0. 0.
Oh, I see what you're asking. I see what you're asking.
So if you have v over z, you would have 0, yes, minus, so the
Whatever the
angle
phase
would
angle
be
is.
0 minus whatever phi you found for z.
Mm-hmm.
All right. So it is 0 minus 0.982. So it'd be plus.
That's what I wanted to ask clarification.
Yeah,
on.
but
So
you see, I don't want you to just think of it of, you know, this being minus, so it becomes plus. I want you to understand why.
Mhm.
It is because you are dividing, so you have you find the difference in the phase angles.
Okay.
All right.
Thanks, sir. Yes, sir.
And of course, the sign that we had in the voltage expression was minus there, so this would be minus. Okay, it's minus 30.
Yes, sir.
All right. And then you're gonna do it for me now for the third harmonic and the fourth. So everybody do that for me. Do it for the third and the fourth harmonic. All right, so I'm gonna start at the bottom of the list. Let's see now. Javier or Javier.
Yes, sir.
All right. Third harmonic. What is that? You mean
Don't have the
complex?
answer, sir.
Pardon?
Don't have the answer.
What do you mean you don't have the answer? That's the first thing. How long ago did I leave the room? 5 minutes? Are you telling me you don't know Z for the third harmonic?
Yeah, man, because I just coming from a practical. This is for my class. I don't really understand
All
what
right, all right. Have fun, sir.
Could I tell, sir?
Rookwood. Mr. Rookwood. What you guys said this thing for, man?
Yes, sir. I'm
Third harmonic.
the third one.
Yeah, man. That was Z3.
Z3.
So you know right that either?
Not really, sir.
Not really. All right.
I'm-
Bora,
I
next.
did 2, sir.
Mr. Rockwood, I have already done 2. Why are you redoing it? I didn't ask you to do that. Bora,
Oh.
Yes, sir.
Z3.
Z3 6 minus J6, sir. The
6
No.
minus J6. All right. Good. So give me the current expression.
current expression 2.357 sine
2.357 sine.
one sine 1131 t plus 0.784854.
785. All right. All right. That sounds okay. Going up the line. Marshall.
All right, sir. For the fourth harmonic, I got
Let's
6.
give me the current. Let's give me the current.
Oh, okay. So I got 2 sine
2.
2 for the current expression. 2 sine 1508t plus 0.643 radian.
643. Did anybody else get 2?
Bro, my skills are wild.
Looks a little clean to me. Did anybody else get 2?
Sir, I got it, sir.
I am pretty sure he got ours.
Yes, sir, I get 2.
All right, cool. So, Mr. Marshall, thank you.
Yes, sir.
So it's actually minus 2, right? I think that would have been So we can now put all these together and write the expression for the current. So the current expression, we start with the fundamental. Yes, so it would be I1. So you'll write this, then minus that. All right, let me use a different color here. Minus that, plus this, and then minus that. All right. So that's the current, that's a Fourier expression for the current. And I think we went up to the fourth harmonic. Yes, so remember, and this is also why I said it's a good practice to look at the harmonics that you have. So you'll know when you have completed the task. So we have completed part A. Does anyone have any questions on this?
Sir, shouldn't it be up to the fifth harmonic, sir?
Is how much we got? Is only 4 with it?
Yes, sir.
All right. Thank you very much. So we can add that. What's it for the fifth? That would be 6 minus J 18 over 5. That's 3.6. All right. Thank you, Mr. Bora. So everybody understand this now? All right. Next, we are asked for the instantaneous power dissipated by the third harmonic. Now, how would I find the power dissipated by the third harmonic? What would be the formula for the power dissipated by the third harmonic?
Sir, I3V.
What's the formula for the power dissipated by the third harmonic?
Sir, it can be P is equal to B3 I3 cos angle 3.
I3.
Yes, sir.
So P3 is V3 I3 cos phi 3. Okay, so what is I3? What would I3 be equal to? Come on, man.
Sir, will it be the 0.785 radians, sir?
Oh, I3. What is I3?
Sir, 2.357.
Good. So it's 2.357. No. Is that correct?
No, you want divided by root 2.
Divided by root 2, because this represents I3M. All right, this is I3M. But this is I3. Everybody good? Good with that? All right.
Yes, sir.
Okay, and V3, third harmonic was 20. So it would be times 20 over root 2 cos, and now we can put in the angle, which is 0.785. Of course, the minus or plus doesn't matter, yes? I mean, if it was minus, it wouldn't matter. So it's 0.7758, right? 85. What am I saying? All right. 785. Okay. And what's that equal to? Of course, gentlemen, you would recognize that if we multiply that, we'll get 2. So you could have simply written I3M V3M over 2. Yes? Cos phi 3. All right, so what do we get? What's the answer? Anybody? It's 23.57 times cos of 0.785.
We get 16.61. 16.61.
You're asking me? Well, you get 16.61. 16.67.
You run off something, sir.
Yeah, I know. But there's no need to round off anything here. You know. Root 2 squared is 2. 20 over 2. That's 10. 10 times 23. 22.3. That's 23.57 cos 0.785. What are you rounding off? People, the calculators won't get tired, you know. Stop this rounding business. One day, you see, I know the question will be asked, you know, when do we, you know, how many decimal places? And all of those arguments come up every year. And my response to that, when you're doing electrical engineering, depending on the branch of electrical engineering you end up in, if you are dealing with electronics, microelectronics, you're dealing with milliamperes, you're dealing with microamperes. So when you round off, you are taking a huge chunk out of the final value. Similarly, if you go to the other end of the spectrum and you're dealing with power engineering, we are dealing with kilo, we are dealing with mega, we are dealing with giga. So when you say I just round off and chop off the 4th decimal place, if you are dealing with megawatts, yes, you would have chopped off a couple hundred watts. Do I make myself clear?
Okay, sir.
All right. I don't need to preach that message again, all right? So that's the instantaneous power for the 3rd harmonic. And then finally, we are asked for the power factor of the circuit. So we want cos phi. So how do we go about finding cos phi? What do we need to calculate? What's the formula for cos phi?
Sir, you divide the power by VI.
So the sum of the RMS times, V1 I1.
So it's P over S, which is equal to IRMS squared times R. We're dividing that by IRMS VRMS. Of course, that just works out to IR over V, but yeah. So the IRMS, well, first of all, let me find VRMS. Do we have any DC component? Do we have a DC component?
No, sir.
No. All right. So it means that our VRMS would be the square root of 60 squared plus, what was it after that? 30. So 30, 20, 15. Please calculate this. Everybody to make an attempt at this. My value
51.33 volt.
51.327.
Not taking any chances, eh?
No, sir.
All right, I'm going to make it even worse. Just put it in the 4 volts. All right. You see, gentlemen, when you give a final answer, then you can round up or round down. You with me? But when you're going through the process, write out the decimal places. All right, and then IRMS would have the square root of, well, I don't remember all of these. 3.1, the 3.1.
3.163.
You sure? I'm sure there was a 2 somewhere. 623, yeah.
Oh.
623 squared plus the 2 point whatever squared plus the 2 point squared plus the 2 squared plus the fifth harmonic, which we didn't work out. What is
1.714?
1.7 squared. And you divide that by 2. All right. So you give me the final answer on that, please.
3.885. Oh, I already did the square root, by the way, sir.
So you add the sum of the squares and then divide by 2 and then the square root?
Yes, sir. 3.885 amps.
All right. Everybody get that? 3 point, what's that? What again?
3.8846.
Thank you very much. Amperes. All right. And so the power factor is equal to 3.8846 squared times 6, or 3.8846 times 51.327. All right. And that's equal to
0.4541. Do we have to go to that many decimal places, sir?
no.
Okay.
Because we're now dealing with power factor. So within the range, 0.45 is quite fine as a final answer.
All right, sir.
Now, because we know that it is a capacitive circuit, we can say leading. However, if it was a combination of inductor and capacitor, you would not be able to say what the final value would be. Meaning whether it's leading or lagging.
Unless you previously calculated XL and X, the total like XL and XC, and figure out which one is larger, right, sir?
As I just said, you will not be able to tell. Because remember, as the frequency changes, so too would XL and XC. The question is, at what point does it move from lagging to leading or leading to lagging? You don't know.
Okay, fair enough.
I was hoping it would be.
All right, so if it's capacitive, then leading, and inductive, then lagging.
It's lagging, yeah.
All right.
Once you have the combination, you won't be able to tell.
All right.
Sure, you're gonna see a point where they change, but I'm saying you won't know when it is net capacitive or net inductive. Because we are not using all the harmonics. Eh?
Yes, sir.
All right. Any other question on what we have just done? Mr. Bora, you had your hand up, but you took it down.
No, sir, it's still there, sir. My question is, sir, for the IRMS, sir, why didn't we put a negative for the second harmonic, seeing that it's a negative value?
You mean this one?
Yes, sir.
All right. So let us say we put negative. Square it. What you get?
You get a positive.
All right. So you answer your question then.
Oh, yes.
Doesn't matter.
Sir, I have a question. In any circumstance, would we ever be required to draw a wave of any sort?
Draw it?
Yes, sir.
Well, no. Well, no such objective. All right. I'm going to answer in a way that will help you going forward. To determine what I can ask you,
Yes,
what
sir.
you need to do is to just look at the syllabus. If the syllabus does not ask you to be able to draw it, I'm not going to ask you.
All right, sir.
If the syllabus says use the Fourier expressions to calculate, it means I must give you the Fourier expression. If the syllabus says develop the Fourier expression, it means that you better go learn Fourier series. So whatever is on the syllabus is what I'm going to ask. And, you know, this is why people think that my modules are difficult. Because for me, once it's on the syllabus, I'm going to test it. Or rather, I'm going to test it. Yeah?
Yes, sir.
Good. So you can rest assured that if it's not on the syllabus, you will not see it in an exam. But if it's there, you can put your pot on fire. It's going to be assessed.
All right, sir.
Good.
Questions?
Uh-huh.
But I'm not sure if they get it. When you find, for the complex way, when you find in phi, if, like, for example, in the polar form, you get a negative. We see where it's being put as a positive. What determine that, sir?
It's not a matter of, you're talking about, for example, when we move from this, from that
Yes,
to that.
when you're writing the current, yeah.
All right. So, in order to answer your question, I'm going to put, my God, I'm getting young. I'm going to ask Mr. Brian, I'm going to test whether or not he understood what I said to him by asking him to explain it.
All right, so we're working with a capacitive circuit. Yeah, and
No. You start on the wrong foot.
On the wrong foot?
Yeah, so you didn't understand what I said.
No, I get why we do it, sir. It's
No,
just explaining it.
Z, it has nothing to do with capacitive or inductive circuit. I'm saying I'm saying I
Uh-huh.
is equal to V over Z.
Yes, sir.
V, based on what we
no,
had, was at angle 0.
Yes, sir.
Z is at an angle phi.
Uh-huh.
So this is going to be at I at an angle 0 minus phi. Because you're dividing two polars. You're going to find the difference between the angles.
Okay. Yes, sir.
So it will be 0 minus minus. That's why you get plus.
Mm-hmm.
If it was an inductive circuit, then phi would be positive. And then when you divide, you're going to get 0 minus. So you're going to become negative.
Okay, sir. So now I get it.
Ah, I realize. You understand that, Mr. Peru?
Yes, sir. Yes, sir.
All right, good. Any other questions? All right. Now, in this instance, what I'm giving you, I'm telling you that it's a full wave rectifier. Now, the fact that it's a full wave rectifier, right? If I'm doing rectification, what's the purpose of rectification? What's the purpose? What we use rectification for?
I get a steady.
To try and
constant.
Yes, sir.
What do you mean by constant? Why are you using them terms? Talk like you're
trying
doing
to get a
electrical
DC wave,
engineering.
sir. Trying to get a DC wave, sir.
Good. So you're trying to convert AC to DC. You with me?
Yes, sir.
Gentlemen, let me tell you something, man. Afraid people can't do electrical, you know? So I don't want you to be hedging your bet about get a smooth, dark plane. If you're wrong, I'll tell you that you're wrong and I'll guide you towards the truth. All right? Don't hedge your bets with me. I'm going to, I'm going to treat it harshly. Anyway, so the purpose of rectification is converting AC to DC. Okay? So the mere fact that that is the purpose, it means that the output of my rectifier must have some DC component. Are we clear?
Yes, sir.
All right. So for the voltage that we have here, the DC component is 50 over pi because it has no sine component to it. All right. The next thing I want you to look at is that looking at the current, that the current expression, do you see a DC component?
No, sir.
No. So if you see no DC component in the current, what is that telling you about the circuit? So I have a DC component. So we're starting out with our analysis, you know, right? And let us, you know, we don't know what the circuit looks like, but I put in a signal and it has a DC component. When I look at the corresponding current, I am not seeing a DC component. What is that telling me about the signal, about the impedance that I'm dealing with?
It wants to be rectified, so
Pardon me?
it means there's something wrong with the signal and wants to be
You can't just
rectified.
assume there's something wrong with the signal. I put in the DC, I put in the voltage. It has a DC component. I'm looking at the output. I see no DC component as we have here. What is that telling me about the impedance through which this current is flowing?
So it is capacitive, sir, because it is blocking the DC signal.
Perfectly correct, Mr. Thompson. The fact that I have a capacitor, what would be the capacitive reactance when I put a capacitor, connect a capacitor to a DC source? What would be the reactance?
So infinite.
Eh?
Infinite
Will
doing
be
right.
Infinity. Infinity, because the frequency is 0. So it means that for the DC component, yes, XC would be infinity, which means that IDC would be 0. So do not be, don't get confused in seeing something like that. It's just the circuit why that is happening. Do I make myself clear? The other thing you could look at to determine or convince yourself that it is a capacitive circuit is that when you look at these phase angles, they are all positive. So if they are positive, it tells you that you're dealing with a capacitive circuit. You see how much clues you get? So there is no need to say, boy, the paper hard. You just look at the information. It's all there.
Yes, sir.
All right. So you have these two expressions. Have you written the expressions already?
Still going, sir.
All right, so you have these expressions. And the question is, or should I say the questions are, let me know when you have the expressions, please.
Yes, sir.
All right. So what we're asked to find, just give me a minute, please. Okay. So we're asked to find the resistance of the circuit, you want the value of the reactive element in the circuit, the active, reactive, and apparent powers supplied by the rectifier. So how do we find the resistance? Any suggestions?
Sir, you use the divide the RMS voltage by RMS current, any one of them?
Any one of them meaning what?
As in any of the harmonics.
All right, so the next thing we need to ask ourselves, which harmonics do we have present?
We have the second, the fourth, and the sixth.
Oh, you know that?
Based on the ratio, sir, of omega.
Well, you know, what is omega?
What do you mean, sir?
What you tell me, what is omega? I don't know, you telling me?
Omega for the second harmonic is 754.
Oh, you know it's a second harmonic.
Oh, okay. Because it comes after the fundamental.
Where's the fundamental?
The DC component.
No.
Oh, wait.
The
Oh,
fundamental
wait.
has the same frequency as the complex wave. So the fundamental must have a sine function.
Okay.
This is DC, so you have DC, fundamental, second, third, etc. harmonics. But I'm saying, looking at this, how do you determine which harmonics we have?
I'm not quite sure, sir.
Anybody else?
Sir, by the amplitude, sir.
The amplitudes can't tell you nothing. The amplitude is just the amplitude. This is 25. This is 12.5 and 5.5. How would you determine the harmonics based on that?
12.5 is 2 times 25.
Yeah, but that has, so what is the relationship between 5.5 and 12.5?
Sir.
Huh?
Yeah, I see it, sir. I see it.
Come on, gentlemen. What are harmonics?
Hold on, sir. Hold on.
I would say it's 3 harmonics are based on the fact that the fundamental is 754.
How do you know it's the fundamental?
Sir, the frequency, sir.
Because it's a multiple of the other angles or the other constant values, sir.
All right, sir.
What is that?
The factor.
Hold on, Mr. Peru. Mr. Bora, come
Yes,
back
sir.
to me. You're telling me that 754 is a what?
The factor are, sir, so basically, sir.
Of what?
Of the other
Oh, sir, is it because we're using a full wave rectifier?
Well, man, we're not reached this
Specifically,
yet, man. I'm saying you need to look at, forget about the fact that we are dealing with a full wave, right? That is of no moment, right?
Okay, sir.
I'm saying to you, look at the expression that you have before you and tell me how you would go about determining which harmonics are present. We know the definition for harmonics, you know. How do we determine harmonics? What's a harmonic?
Sir,
Oh, this is just telling me that you haven't looked at the first lecture.
yes, sir. A variation of the fundamental at a different frequency.
Variation. I gave you no such statement. What is a harmonic?
Sir, sine waves with frequencies that are exact multiples of the fundamental.
Okay, no. So looking at this, yes, what are the, I mean, whether you want to use the frequency or the angular frequency, whether you want to use F or omega, what's the relationship between the omegas in the voltage expression?
The
omegas are double of the previous one.
Yes, sir. Related by multiple.
So this is 2 times this. What else?
3. The other frequency is 3 times.
Okay.
Oh man, the other frequency is 4 times. 4 times the fundamental.
No, it's 3
times, sir.
It's 3 times the first one.
It is?
So this is 754.
Yeah, it's 2.
Huh? So you're saying that this is the fundamental?
Yes, sir.
Yes, sir.
Are you saying this is the second harmonic?
Yes, sir.
Are you saying this is the
third
harmonic?
I can work with that. Even though that is not totally true, but yeah, I can work with that.
Oh, what is the truth, sir?
Huh?
What is the truth?
I'm saying I can work with that, assuming, you know, But what I can tell you, yes, that this is really the second, fourth, and sixth. But you wouldn't see that. But based on what is here, this is three. This is, if you count this as a fundamental, this is indeed 2 times, and this is indeed 3 times. So I wouldn't have an argument with you on it.
Okay. So
that's the point I'm making. But because I know from a full wave rectifier, it has second, fourth, sixth, we would be all right. So if you tell me 1, 1, 2, 3, I am cool with that.
So then
is it because would it be because the third, fifth, and so on would have been rectified, so you would not actually have it?
No. It's not about no. Remember, the full wave the full wave waveform looks like this. Yes? So when you find the Fourier expression for that, this is what you're going to get.
So sir, when approaching another question like this.
So one sec. So Bn would be 0. So you'd only have A0 and the An values when n is even.
Repeat that again, sir.
Repeat that last part, please, sir.
I'm saying this waveform, that's a full wave rectified waveform. When you find the Fourier series, if you go back to how we define a Fourier expression, yes, or the coefficients, you would have had A0, An, and Bn. So I'm saying to you that in this instance, yes, the A0, of course, would be your DC component, and your An values would be here. So the Bn values would be equal to 0. Back in the first lecture.
Yes, sir.
You have to go back and look on that video again. Anyway, so here we have somebody had said earlier we would take any 2 of the any 2 harmonics. Somebody said that earlier, right?
Yes, sir.
Who was that?
Me, sir.
All right. Explain that. So tell me what exactly we need to do now.
Give me 1 second, please.
We're working out.
No, not working out. I was because I had the papers all over the place. All right, sir. So because we already defined what a harmonic is when we are finding the impedance by dividing the RMS voltage over RMS current at any other harmonics, the ratio.
Why are you worried about harmonic? RMS. That's not important, because remember, if I divide to find the RMS value of the voltage, I divide it by √2.
The amplitude, my apologies.
No, you don't have to apologize. I'm saying if you found the RMS, you'll be dividing the amplitude by √2.
Yes, sir.
For the current, you'd also be dividing it by √2.
Yes, sir.
So when I divide the two, both √2s will disappear. We cancel each other. So it means that Z is equal to V over I. Whether you want to use V1M or I1M,
the ratio will always be the same.
Or you want to use V2M over I2M, right?
Yes,
you'll get the same thing. All right?
Yes, sir.
Same thing in terms of the R value. So here, if you want to use 1M, we'd have 25. And that's at an angle of 0. Yes. Are we dividing that by I, which is 2.0113. So that's 2.0113 at an angle of 1.326.
Okay.
326. Okay?
Yes, sir.
And what does that give us?
12.43.
12.43. You're chopping off the decimal places again.
Sorry. Before I round it up. 2.013 at an angle.
All right, so that is 25 divided by 2.0113 at an angle of 1.326. All right, that gives us 3 minus J12. So that gives us.
Well, you said 12.14
3 minus J12.
Oh, but I'd round it up. I'd round it up because I'd used 3 decimal places and the number behind that was 7. That's why I just rounded it to 2 decimals.
Yeah, man. All right, the 12.43 would be all right.
Okay.
At that angle, of course, that would be minus. Yes, minus 1.326. Okay. And this is what you'll get. 3 minus J12. So the question is, what is R?
3
ohms. And the J12 would represent what?
The capacitive reactance.
And how do you know it's capacitive?
Because there's a DC component in the voltage. Sorry,
well, that is one. But looking at the impedance.
Oh, the minus.
The minus. So you know from the minus that it is capacitive. So you'll find this would be XC. So from that you can find C.
Yes, sir. That's the second part.
Did I lose anybody? So we would have found this and that in one go. So you get 6 marks already. And this is all you have done. And you all think networks hard.
So I want to say confidence, but
Yeah, but you remember where we started? You all think, I tell you, I don't like talking. So therefore, when I say something, it is wise, it is good for you to take note. I don't give you or share statements with you because I just want to share it. I said the only way to gain confidence is by repeat activity. Practice. You will never become confident in networks without practice. And most of the things I am getting from you when I look at these assessments, it tells me that one, when I finish class tonight, half of you just go to your bed and put on the book. And you won't take it up again until next week, Tuesday. Well, there is no more next week, Tuesday for you. But that's how you treat networks. If you do that, gentlemen, you're going to fail. I'm sorry, I am one of those lecturers who just not beat around the bush, the bush too. Walk around bush, it's far. So I cut to the chase. If you are not going to practice, you're wasting your time with this module. However, if you decide to practice and put in the time, do the questions, even if you do a question and you have gotten it right, take my foolish advice. Do it 2-3 times until you're able to do it in 15 minutes or less. So if you can't do a full question in 15 minutes or less, it means that you have not understood the concepts.
Yes, sir.
There's a word for preaching me going on with tonight. But anyway, so part C, you know, and you see the bulk of the mark, the 15 here is for the active power. So the active power, I mean, that's 15 marks are giving away, you know. The active power, P, is equal to IRMS squared times R. You know what R is? Yep. So you go back to your current expressions. Yes. And so IRMS square root. Now this is where it becomes tricky. You're gonna put in, of course, the IDC is 0. Okay? Remember we didn't have a DC component. And then for the first one, it would be 2.0113 squared plus 1.8634 squared plus 1.10715 squared. Divide that by 2. Define RMS. VRMS. All right. Now I'm doing one with the DC so that you'll understand the difference. This would now be 50 over
sir,
pi.
why use 1.10715?
Oh Lord. Where does 1.11? I misread it. So it's 1.111.
All right, sir.
I don't know. That was the angle. 1.1111 squared divided by 2. For the VRMS, you have 50 squared plus, because remember now, this is the 50 over pi is the DC. So you have 25 squared, 12.5 squared, and 5.555 squared. You divide these by 2. So your squared rows, add them, divide by 2, and then you add it to the 50 over pi all squared. All right, because remember, the reason we are dividing by 2 is because the 25 would have been over root 2. The 12.5 would have been over root 2, similar to the 5.55. And so once we have these, then the rest of the question can be completed, which is what you're going to do on your own. All right, gentlemen?
Yes, sir. And I'll just use that to find what was the last one? Oh, the rest of them, the powers.
Yep.
Yeah.
So from that, of course, you can find the power factor, which means that if you know the power factor, you can find S. If you know the power factor, that will be cos phi. Yes. And to find the reactive power, you need sine phi. So you just need to find the inverse of that value, the inverse cos, find phi, and then you have the sine phi. All right, so I'll leave you to complete that. And that's it from me. And guess what? That's it for the module.
Sir, you can,
pardon?
Sir, you can go back to the questions. I can finish right without 1 minute, sir. I didn't. The last thing to determine. So yes, sir. Thanks.
All right, so that's it for the module. I've already given you sent you a message regarding the assessment number 3. Let me see now. Next week Tuesday is the last day of school, right?
I believe so, sir.
When did I say it's the assessment? Is next week Wednesday?
No, I think Wednesday is the last day because I have a class. I think Wednesday should be the last day because I have a class, I think, on that day. Final class.
I didn't hear that.
I think Wednesday is the final day, isn't it, sir? Because that's when the semester started on Wednesday.
It's supposed to end on the Tuesday because lecture started on a Wednesday. for the whole Thursday thing.
Oh, okay,
Anyway,
sir.
so we go Wednesday to Tuesday. But if a lecturer is cheating on the Wednesday, then so be it. Yeah, so tomorrow I will have the other group, and it is for them to go through this material. If you want to join them, you are free to join them. I am only going to be there to field any questions and provide any clarifications that persons require on complex waves. And of course, assessment 3 will cover AC circuits, resonance, and complex waves. All right. And then after that, once I get the date for your final assessment, I will let you know.
So you said tomorrow's class is just gonna be there to field question?
Is it me? You're very low. Go again.
So you said just now that tomorrow's class you're gonna be there just to field questions?
Yeah, man. If you
Okay.
want clarification on complex waves, I'll be there to do that.
All right, sir.
Because this is it. They will be required to look at the video for what we have done tonight. And, you know, if they have any questions, then we'll go through it. All right, gentlemen, that's it from me. Have a good evening.
Yes, sir. Take care.
All right, take care, sir.
Yeah, cool.
Take care, sir. Thanks.
All right.